All right. Thank you, Joe. And I'd like to start by thanking Joe, So, and Yunshan for their kind invitation. I really appreciate the opportunity to present our work here. Even though you gave me the worst possible slot to give a talk, I still really enjoyed the workshop. So thanks for that. As Joe said, I'm going to talk about non-local magnon-polaron transport in yttrium iron garnet. And this work has been done in our lab in University of Groningen, the Van Wees lab, in collaboration with the lab of E.G. Saito in Tohoku University. And in particularly, I should mention Koichi Oyanagi, who is a grad student in the Saito lab, and he basically did most of the work on the Japanese side, whereas I was in charge of the project on the Groningen side. So we've already heard quite a bit about magnon-polarons in this workshop. In particularly, the talk by Ka Shen, of course, was very nice. Introduction to this. But just to remind you, a magnon-polaron is nothing more than a composite quasi-particle formed when magnons and phonons hybridize. And just my very simple picture of what is behind all this, that is the magnetoelastic coupling. So this is a really super simple illustration that I stole from Gerrit Bauer. So if you imagine a lattice of atoms which all carry a spin. Now if you would have an acoustic wave passing through this lattice without any magnetoelastic coupling, what would happen is that the atoms just move like this without changing their spin direction. Now if you turn on the magnetoelastic coupling, then actually this lattice distortion would also induce spin dynamics in the lattice. So you get, instead of only moving the atom up and down, you also change its spin direction. And the opposite is, of course, also true. So if you excite a spin wave in such a system, you will also affect the lattice dynamics. Now this in itself is nothing new. It was first described by Kettel in, more than half a century ago. But despite the fact that this is quite well known, it still causes surprises even nowadays. And there's been a lot of work, also recent work, on the magnetoelastic coupling, in particular in magnetic insulators. Where I should of course also mention the work that Vitali presented in this workshop, where they show that this magnon-phonon hybridization can lead to some bottleneck effect in yttrium iron garnet. So just to paint a picture once more, what we're interested in is really the strong coupling regime. So that means that if you look at this dispersion for phonons, which is this linear line here, and for magnons, which is parabolic, then we're interested in really these points in K-space where the magnon and phonon dispersions cross, or in the case of very strong or of large magnetoelastic coupling, instead of crossing, they actually form an anti-crossing here. So at these anti-crossings, your excitations are fully mixed quasi-particles, which consist of both magnons and phonons, and which we now call magnon-polarons. All right, so what we were interested in, after learning about all these nice recent results that I just flashed on the previous slides, is what does this now have a consequence for magnon spin transport? And so as was already showed by Bosco and co-workers, this indeed has a consequence if you are exciting magnons coherently. So what they do is they have a YIG sample, and they excite it with microwaves via parametric pumping, and then you can indeed detect the accumulation of hybrid quasi-particles at the anti-crossing between the phonon dispersion and the magnon dispersion. But well, our approach is a bit different because we drive the system incoherently. in particular via spin Hall injection of magnons. So this is what we call electric excitation. And the idea is we have a YIG film with 2 platinum contacts on top, and then we pass a current through this platinum contact, and via the spin Hall effect, in this way we can generate magnons in the YIG, which we can detect in the detector. And I will get back to this in more detail later on. And of course, you can also drive the system thermally via the spin-Seebeck effect. So then you have a platinum YIG bilayer system. You apply a temperature gradient normal to the plane of the film with an in-plane magnetic field. This will excite the lattice dynamics in YIG, and it can pump a spin current into the platinum, which you can detect as a voltage via the inverse spin Hall effect. So in my talk, I'll be mostly focusing on this incoherent excitation of magnons. And then what we want to study is what is the role of the magnon-polaron or the magnon-phonon hybridization in these, if we excite magnons in this way. So this is the outline of the talk. I just gave you a very brief introduction, and then I will talk shortly about the earlier results from the CYTO lab, where they studied the role of magnon-polarons in the local spin-Seebeck effect. Then I have to switch gears a bit and talk about non-local magnon spin transport in YIG, which is basically going to be our probing technique. And then in the end, I'll combine these 2 ingredients to talk about non-local magnon-polaron transport. All right, so magnon-polarons in the local spin-Seebeck effect. And what I mean when I say local spin-Seebeck effect is always the heater-induced longitudinal spin-Seebeck effect, where we have this, stack or bilayer stack, as I just described. So yttrium ion garnet platinum, usually on a GGG substrate, and via the external Peltier heating and cooling elements, which are not drawn here, you can apply a out-of-plane temperature gradient. And if we now look at the dispersions for magnons and phonons in the system, you get a picture like this, where you have the quadratic dispersion of the magnons, and you have 2 linear phonon branches. So one is the transverse acoustic phonon branch and the longitudinally acoustic phonon branch. And so this is kind of sketched over here, where your transverse acoustic phonons correspond to this kind of motion, and longitudinally acoustic phonons correspond to this kind of longitudinal motion of the lattice. And then the hybridization between magnons and phonons happens at the anti-crossings between the phonon branch and the magnon dispersion. And now what is kind of neat about this is that via the external magnetic field, we can actually shift the dispersion curves shift the magnon dispersion to basically to a point to reach a field where the effect of this magnetoelastic coupling is maximized. So basically, by applying H, you can shift this magnon curve up and down. And this is kind of illustrated here. So here, if we are below the resonance field, we get this kind of picture that I already showed you before. By the way, this is taken from work by Benedetta Flebus in the group of Rembert Duinen, where K was also involved in this work. And if we actually we set the external field to be right at the resonance field, we change the picture to look like this, such that you will form an anti-crossing between magnons and phonons over a relatively large region in K-space. So, well, basically the argument is that now you will just have a larger fraction of your magnon population which participates in the hybridization, and because this fraction suddenly increases or is maximized at this field, you get a kind of resonant little feature there. So you notice it's a small feature, and the reason for this is that the majority of the magnons, which are responsible for the spin-Seebeck background voltage, you could say here, they are still not really hybridizing. I mean, the largest fraction of the magnons is still just pure magnons, but you just have a significant fraction here that is now hybridizing with the phonons, which leads to this, this little enhancement of the signal right at the resonance field. And in the original experiments by Kikawa et al., they call this the point touching condition, such that, you know, yeah, basically what I just explained. At that field, the interaction is maximized. And now basically the explanation for their observations was that basically relied on only one parameter, which was the ratio between the impurity scattering potentials for magnons and phonons, respectively. So they found that the local spin-Seebeck effect shows a peak when this ratio is larger than 1, or in other words, when the magnon lifetime is shorter than the phonon lifetime. So in this sense, you could kind of naively think about it as magnons being dragged along by phonons which live longer, which is why you get an increase in signal. And the opposite is true. So for the opposite case, so when magnons are undergo less impurity scattering than the phonons, then you would get a dip in the local spin-Seebeck effect. And that was kind of the only parameter which they needed to explain the experiments. Yes?
But it's counterintuitive, but because this magnon is responsible for spin current. If magnon's lifetime is shorter than phonon lifetime, then magnon decays. Because magnon is the particle with the spin.
Right. So, but the thing is that you're right. But now, because the two hybridize, the magnon-polarons will give an enhanced. So by hybridizing with the phonons, you could say that the effective lifetime of the magnons is increased, which increases the spin current. Yeah.
Let's say, put it this kind of argument to the extreme case, is that if we assume super strong coupling between these two, then we get kind of a super strong. So what kind of thing can we imagine if there is super strong coupling between these two and you have this touching point?
Let's see. So I would say, so in this, to get this hybridization, you already need a certain value or a certain strength for the magnetoelastic coupling. And actually, I'm not really sure what would happen if you make it even stronger, because basically the argument of the k-space argument doesn't really change, right? It's only, well, if you make the coupling stronger, perhaps you could have a larger fraction of the magnons participating in the hybridization, but I'm not 100% sure actually.
Actually, for experiment, this kind of thing is important because this material, I think it actually is a very weak magnetoelastic coupling, right? It's very usually like if you choose some material like a spin, like a ferrite, so you can see pretty huge magnetoelastics.
Yeah, that's true. There are materials which have a larger.
The relevant point is the magnetoelastic coupling, the ratio of magnetoelastic coupling to the damping. Because whenever we talk about strong coupling to hybridization, what matters is how strong is your coupling term as compared to the damping term. Because the damping term kind of gets rid of this hybridization.
Yeah.
So in that sense, with this more correct metric, I think it is still very strong magnetoelastic coupling system. And as for the reduction of spin, you can imagine that the hybridized particle effectively has been h power by 2. So you're right that you get reduction of spin by half, but the velocity was enhanced by much larger because the magnon velocity was practically zero at that. It was flat, right? But because of the phonon, this particle has a velocity enhancement of several orders of magnitude. The spin decrease was only by factor of 2. So overall, there's an enhancement.
For that second part of the velocity is
Yeah, the group velocity of the magnons and phonons is the same.
Yeah, okay, yeah. When you have the quantization, I see. Yeah, you're right. So there's the velocity, there's the damping.
Because it was of like light, stronger magnetoelastic coupling, that the peak would be like broad. Yes.
Sorry?
So the peak,
Yeah, so then will be
the
bigger.
peak would be like broader.
Yeah, there will be bigger phase space.
Yeah.
If you have the same damping here.
Right. What's actually being measured when you measure that peak? Is it magnon-polarons impinging on the platinum and that's what you measure, or does it have to decay into a magnon before it hits the interface?
So I think the current interpretation is that it really are magnon-polarons that impinge on your interface, which then cause the same spin flip scattering. Yeah. All right, so now I want to switch gears a bit and move to show our kind of experimental technique, which we're going to use to probe magnon-phonon transport, which is basically non-local magnon spin transport in yttrium ion garnet. So the idea of such a non-local experiment is the following. So this would be a side view of a device. So we take a film of yttrium ion garnet, we sandwich it between two contacts, pass a charge current normal to the board through one of the contacts, and then via spin Hall effect, this generates a spin current towards the yttrium ion garnet. But what happens at the interface is that the electrons have to scatter back, and in doing so, there's a finite probability that they will flip their spin. So spin up gets scattered into spin down electron, and this difference in spin is then transferred into the YIG as a magnon. So the magnons then diffuse in the YIG until they reach the other interface where the opposite process happens. So magnon gets absorbed by a spin down electron, which gets scattered into spin up. And this is equivalent to sending a spin current into the platinum, which via the inverse spin Hall effect then generates a charge current or charge voltage if you measure in open circuit in this platinum detector contact. So our actual geometry is a bit different because making such a sandwich turned out to be challenging. So instead we use a lateral geometry where we have an extended YIG film and we put two platinum contacts on top of that film. But then the mechanism is still really the same. So we drive the current here and then we measure the voltage over this contact here. And then we put the sample in an external magnetic field, which is basically only used to orient the magnetization of the YIG relative to the polarization of the spins of the spin accumulation that we're supplying at the interface. And so what you get if you rotate the sample in the external field like this is the following curve. So here you have the angle alpha, and here you have the non-local resistance, which is just the voltage we measure over the current that we send. And you see that it fits nicely this cosine square alpha dependence. And the reason for it is as follows. So this is a top view of the device. And what we do is we pass a current through the injector, which generates magnons, or generates a spin accumulation polarized like this via the spin Hall effect, so mu I. Only the component which is parallel to the magnetization will generate magnons in the YIG. So this gives us our first cosine alpha term. And then these magnons diffuse to the detector, where they induce a spin accumulation mu parallel in the detector, but because of the symmetry of the inverse spin Hall effect, we only measure this component, mu d, and that gives you a second cosine alpha term, and then the total signal is a product of the two, so we end up with cosine square alpha. And now I should say that in recent years there's been quite a lot of progress doing these type of experiments, also by other groups. So for instance, the Groningen group has been very active in using the same geometry, but of course also by, as we saw in the talk by Felix, they're also using this lateral geometry right now. And even Katrien Ganshorn showed that you can perhaps even build some kind of logical element using this this geometry if you increase the number of strips you have from 2 to 4, basically. You can also use this kind of experiment as a tool to study magnon transport in different materials. For instance, gadolinium-ion garnet, and in our group we've used it to study nickel ferrite. And then finally there's also two groups who've used, who took the real sandwich approach, I should say. So instead of making a lateral geometry, what they did is first put the platinum, then grow a YIG film on top, and then deposit another platinum film on top. So you make the real sandwich structure, and then you can play the same game. I should say that what they typically find a much lower quality of the YIG film, so much shorter diffusion length, because it's very hard to grow really nice crystalline YIG on top of a platinum film. And so in devices like this, we not only generate magnons electrically, but also thermally. Because when we are applying a current here, we're of course heating the injector electrode. And this creates a temperature gradient in the yttrium-ion garnet, which via the Spin-Seebeck effect drives a magnon spin current again, which we can then detect in exactly the same way using the detector. So this is referred to as thermal magnon injection. But the good thing is that we can actually separate electrical and thermal injection because they depend on the current in a different way. So electrical injection is linear in the current, and thermal injection scales with the current squared. So this is very nice, and we use a lock-in technique to measure these two independently in the same measurement, basically. I won't go into the details now, but you can ask me if you like. So what you get if you do, again, the same angle-dependent measurement, but now instead of the electrical signal, you measure the thermal signal, you get a picture like this, which now shows also different symmetry. So now it's basically a cosine alpha dependence. And the reason for this is that all of a sudden our injection process no longer depends on the angle between the YIG magnetization and this injector. So we're basically generating heat here, which is constant in angle. The magnons you generate still diffuse, and they are picked up in the same way. So we are left with only this cosine alpha term, basically. And if we now compare these two injection methods, and we vary the distance between injector and detector, then we can basically have a probe to figure out how the magnons are transported and how they decay in the YIG. And so that's what we did. Basically made a lot of devices with a lot of different distances. And here you see plots of the basically distance between injector and detector, which goes up to 40 microns here. And then this is the electrically generated non-local signal. This is a thermally generated non-local signal. And you see that signal decay is really remarkably similar in these two cases. And in particular, if we now look at the long distance regime, so for distances which are relatively large, we get this real exponential decay of the signal. Basically, if you now look at the slope of this tail, this will tell you or give you the characteristic length scale over which the magnons can travel in a device. or in the YIG before it decays. So this is what we call the Magnon spin diffusion length, and so you can extract them either from the electrically generated signal or from the thermally generated signal, and they turn out to be, well, within our experimental accuracy, I would say that they are the same, and they are around 9 micron. However, if you look a bit closer at this, in the short distance regime, it's what we call the diffusive regime, so their Magnon relaxation is not the most important decay mechanism yet, but it's really purely diffusive transport, then these two turn out to be quite different. So here I show a close-up for only very short distances of the electrical and the thermal signal. And now I switch back to a linear scale because we found something very peculiar in the thermally generated signal. So maybe first the electrically generated signal scales with 1 over the distance here, which is basically what you expect from a spin diffusion picture. But the second harmonic signal seems to have this maximum here, and then it even changes its sign here. Now, when I first measured this data point, I was a bit scared, and I think I checked it at least 30 times to make sure that I didn't do anything stupid and or change some connections or whatever. But no, it was really negative, and this really puzzled us for a long time. We didn't know what was going on there. So that's why we've now recently been looking into what's happening here on a really short distance scale. And we actually had a hunch because we noticed that in electrical generation, the magnons you are generating really at the surface or at the interface between platinum and YIG, so it's very localized. But in the thermal generation, of course, your temperature gradient is much more spread out in the YIG film. So we thought it might be related to this effect that you are having a much more delocalized excitation here. So what happens if we increase the thickness of the YIG film? Perhaps we can also tune what's the behavior of the signal in this regime. So this is what we then did. In particular, most of the work was done by Juan Shan, who's a colleague, PhD student of mine, but I was also involved in the project. So basically we made a lot of devices again on a lot of different, or on several different thicknesses of the YIG. So here you see these dots are for 200 nanometer thickness, which is basically the same as what we used in the original experiments. And then we make it thicker and thicker from 1.5, 2.7, all the way up to 50 microns. So here you see the thermally generated non-local signal as a function of distance again. And you see that indeed, as you make this YIG thicker and thicker, you push the distance at which the signal changes its sign to further and further distances. And in fact, it turns out to scale more or less linear with the YIG thickness. So as you can see here. And then, so later work by other groups also showed that it not only depends on the YIG thickness, so this is all done at room temperature, but it actually turns out to also depend on the temperature. So this is work, again, by the Groningen group, where they show this sign change distance as a function of temperature. And you see that it reduces as you reduce the temperature. So now to understand what's going on, we turned to numerical modeling. So we wanted to build a finite element model of our devices in which we could also probe this effect of YIG film geometry. So if we want to be able to play with the device parameters to see if we could reproduce this kind of behavior of the non-local signal. So basically the core of our model is this linear response relation for the Magnon spin current that's given here, and the Magnon heat current, which is given here. And you can see that these two are driven by gradients in the Magnon chemical potential and the Magnon temperature. Now there are a couple of assumptions underlying, or a lot of assumptions actually underlying this model. The most important one is that magnons will scatter very strongly with phonons, and they will exchange energy very efficiently. And this means basically that your Magnon temperature is equal to your phonon temperature throughout the device, well, within a very short length scale. So basically after the relaxation length, energy relaxation length for this parameter is on the order of 1 nanometer. So you can see we have the Magnon spin conductivity here, which basically tells you how efficient gradients in mu drive a spin current. And we have the heat conductivity, which tells you the same for the heat current. And then we have here the spin-Seebeck term and the spin-Peltier terms in this equation. And now, before I show the results of this model, I want to first paint a qualitative picture, because I hope that will be easier to understand. So here I draw again a side view of our device. So we have an injector, we have a YIG film, and we have a GGG substrate, basically the bottom of the GGG. So this is not to scale. GGG is usually much thicker than YIG. The bottom of this GGG substrate is thermally anchored, so we know the temperature we have there. And then we heat the injector up to some temperature by the Joule heating of the current. Now we create a temperature gradient here, which drives a Magnon spin current radially away from the injector. And now the interesting thing happens at this interface between YIG and GGG, because of course the heat current can flow very nicely into the GGG, but Magnon spin current cannot. So magnons will accumulate at this in the bottom part of the YIG. And because they are driven away from the injector by the thermal gradient. And likewise, they are depleted, or they move away from this region directly below the injector contact, well, because you drive them away via the thermal gradient. So this is the picture that you then get. You get some region with a positive chemical potential at the bottom of the YIG film, and a negative chemical potential directly below the injector. But of course, this then again establishes a gradient in mu in the thickness of this, over the thickness of this YIG film. So you get some diffusive backflow current of magnons from mu plus to mu minus. And we believe that these kind of two mechanisms, of course, in reality you cannot disentangle them like this, but we believe that this is what, in the end, results in your sign change at long distances. And in fact, if we solve the model, these equations in our finite element model, then we get a picture like this. So here, this is again the side view of the device. So now we have a reasonably thick YIG film, such that we can actually see the effect very clearly. So this is 2.5 microns, and this is the X position basically. Here you see the injector. You see indeed this region of negative chemical potential directly below the injector. And here this white ring that you form, that is the position at which the signal exactly becomes 0, and after that it changes sign to a positive chemical potential. And this, so you have to tune then the parameters of the model. So what we get is that in this case it's approximately equal to the thickness of the YIG. And now indeed we can also understand why this is related to the YIG thickness, because if you make the film thicker, basically you reduce this thermal gradient here between mu minus and mu plus. So this diffusive backflow current will become smaller basically, and that causes this region mu minus to spread out further into the YIG. Okay, so basically we then varied the thickness of this YIG film, and we see indeed that we get this kind of linear relation between the sign change distance and the thickness. I should say that this does not give any quantitative agreement yet. Our model is not quantitatively fitting to our experimental data, but we seem to reproduce the qualitative behavior.
Essentially here is the ratio is 1, right? Distance to thickness.
Yeah.
We get 1.2.
Right.
It's not that bad.
No, but I mean, because you can calculate. Yeah, no, that's right, but you can calculate the spin current you expect to get in your detector. And what we initially wanted to do was really achieve quantitative agreement between the signal we measure and the simulations. But this turned out to be extremely difficult because there's so many parameters involved, like the conductivity of the YIG, but also the interface between YIG and platinum, the spin Hall angle of the platinum. So yeah, you can spend forever tuning these parameters and still not get agreement for. So yeah, that's what I meant. I agree that the qualitative picture is quite okay, and I'll show some more of this later. Okay, so now I want to move to Magnon-phonon transport. Actually, I still have a bit of time, right? Oh, okay, I'll be really quick then, sorry. Okay, so just briefly, what happened again in the local spin-Seebeck effect, so this configuration, there we saw these kind of peaks at the resonant field in the local spin-Seebeck voltage. And you see that the spin-Seebeck signal is enhanced at the resonance field. Now we look at this non-locally. We basically do the non-local spin-Seebeck experiment, and we get a similar feature. So we indeed see this enhancement of the signal at the resonance field. However, so this is for a distance of 2 micron between injector and detector. Now we move to a larger distance, and all of a sudden we see something different. We still see a small effect at the resonance field, but now all of a sudden, instead of enhancement, we get a suppression of the signal. And I agree it's not that obvious to see. You really have to look at the numbers here. But here you see the signal at the baseline, it's higher than the signal at the resonant field. So the signal is suppressed there. And of course, this is also related again to the sign change that I was talking about. So you see that also the sign of the spin-Seebeck signal for short distance is again opposite to that for longer distance. So this was measured in this 2.5 micron film. So the sign change point is somewhere between this 2 micron and the 6 micron. So you have two things happening. One is the sign of the background basically flips, and the other one is that the role of this magnon-polarons changes from enhancement to suppression. Okay, so I think I'll skip this for the moment, and then talk directly about the distance dependence again. So basically what we see at short distance, we get peaks in our signal, and at long distance we get dips in our non-local signal. And now I should emphasize that these distances are all measured on the same YIG sample. So we're quite sure that we're not changing the ratio between the impurity scattering from magnons and phonons. So we're not changing this parameter, which in the local configuration basically determines whether you get a peak or a dip. So in our samples, we always get, if we measure locally, we always get peaks, basically. So we did not understand what's going on here at long distance. Right, so in this red, so this is the non-local signal at low field, so what you would normally call a non-local signal amplitude of the non-local spin-Seebeck effect. And this is the amplitude of the resonance, or basically the height of the peak that we measure. And in the red region, then this corresponds to a peak, and at longer distances, so beyond the sign change point, it corresponds to a dip. And now we wanted to understand what's going on based on our model again. And the explanation that was originally given by Kekawa et al. Was that you get an increase in your spin-Seebeck coefficient, so that would be your L here in this case. However, if you increase L, basically you're just increasing the efficiency of converting a thermal gradient into a Magnon spin current. So you're basically just increasing all Magnon generation, and this would not give you a dip at large distances. So this is not enough to explain our observations, basically. But at a similar time, again, Benedetta Flebes, also in collaboration with K, they published a paper in where they do more elaborate calculations, and they show that apart from only the spin-Seebeck coefficient, other transport parameters can be affected by this hybridization as well. So, for instance, the Magnon spin and Magnon heat conductivity, they also show these little peak-like features at the resonance field. So this is, by the way, the Magnon-polaron contribution to the spin-Seebeck coefficient, which shows this strong peak at the resonance field for low for TA phonons and LA phonons. And here you see the same feature in the total spin conductivity. Okay, we thought, well, maybe if we include this effect, we can actually understand what's going on. So then the story is as follows. If we get some resonant enhancement of sigma at the resonant field, then we might increase this backflow current between mu plus and mu minus. And if you increase the backflow current, then basically both your mu minus and your mu plus would reduce in magnitude, because you basically the magnons from mu plus replenish the depletion at mu minus. And this could cause dips at large distances. It's not trivial that it does. It depends, of course, on how much you actually increase your conductivity. So we try to compare our model and the experiment. So first I show again this background non-local, the amplitude of the non-local signal at low fields. And this is what we get from the model. So you see that indeed we reproduce the sign change distance relatively well, but the magnitude is completely off. So it's not quantitative agreement. And then we include this enhancement of zeta and sigma in the model. And we vary the ratio between their enhancements. So basically, delta describes how much sigma and how much zeta are enhanced at the resonance field. So delta of 1 means they're enhanced in the same way. Smaller than 1 means sigma is more strongly enhanced. Larger than 1 means zeta is more strongly enhanced. And then what we get is basically these results. So by changing delta, you can change the amplitude of your resonance rather strongly. So this green curve shows delta equal to 2. You see that at some point it becomes negative. And that's basically what we not observe in our experiment. So negative amplitude at large distance would mean also a peak at large distance. But by reducing delta, we can shift this curve upwards such that at some point, for some value of delta, we have a purely positive amplitude, which is also what we observed in the experiments. And so basically we find qualitative agreement for delta between 1 and 0.5, which basically means that your sigma has to be enhanced slightly more strongly than your spin-Seebeck coefficient. Right, so that was what I wanted to say, and I think I'll end here by flashing this conclusion slide. So thanks for your attention.